Last section in 1.1 we talked about categorical data and how to display it with graphs. In 1.2 we're going to start displaying our quantitative data with graphs. The first type of graph you can draw is a dot plot, and we've done these in class sometimes with the activities we've done. It's the easiest one to draw and the easiest way to show quantitative data, especially when there's not that many points. So you start by drawing a horizontal axis. You have to have it labeled with the variable name and an appropriate scale along the axis from minimum to maximum value. Then every time you have a data point that fits inside one of your x-axis ranges, you put a dot. You want to stack them and make them even in size. So for example, number of goals scored in the 2012 women's soccer team. We've got 0, 1, 2, 3, 4, 5. Then there's a large gap for 13 and 14. So you can't put 13 and 14 close to the 5 because it has to follow the same scale. So if we want to look at the distribution of any type of graph that we have, then you're going to look at the overall pattern, which could include the shape of the graph, where the center of the graph is, the variability, which we'll talk about in a minute, and any unusual points or outliers. So you always want to talk about these things when you are describing any type of graph or distribution for quantitative data. So to describe the shape, you could have a symmetric graph where the left side and the right side are close to mirror images of each other. No graphs are perfect, and that is why you always want to use some sort of approximating terminology, like it is approximately symmetric, or is almost symmetric, or is somewhat symmetric. You want to use these unsure words. And then you could have a skewed to the right graph. A skewed right graph means most of the data is on the left and you have a tail on the right, and we'll see a picture of that in a second. And then a left skewed graph is when the tail is on the left, so it's skewed to the left because the left side of the graph has fewer points than the right side of the graph. So this first graph down here is roughly symmetric. The middle one is skewed to the left. Notice wherever the skew is, that's where the tail is. So follow the tail, and that's the type of skew that you have. And then you've got a right skew on the last graph shown here. So here's some other types of distributions you might see, and you need to know some of this terminology. You've got unimodal, that means there's only one mountain peak. You've got bimodal, that's where there's two peaks. And then uniform is where it's pretty much straight across. There's no peaks in it at all. So let's talk about measures of variability and measures of center. So a less varied graph has a smaller range. The data points are closer together or more concentrated in one area. A more varied graph has your data more spread out across a range. So here are some measures of variability you can use to help you. The range, the standard deviation, which we'll talk about in 1.3, and the interquartile range, which we'll talk about in a little bit. Measures of center, that would be your mean and your median. When you are comparing distributions, you always want to talk about the shape, the center, and the variability, along with some possible outliers. You always want to discuss this for both graphs and then compare them. So two things you need to have whenever you are comparing distributions is all of the shape, center, variability, and possible outliers for each graph and how they are related. And an easy way to lose points on a question like this is to not actually use context. You can't just say the shape is. You would need to say the shape of the distribution for household size in South Africa is skewed to the right. The shape of how the distribution for household size in the UK is roughly symmetric. And then you could say something about the variability. Household size for the South Africa is more varied than the household size for the UK. And so you want to be able to compare the two while also giving all four of those possible things. When you talk about the outliers, there's not always going to be an outlier, so you don't always have to mention it if there isn't one. For South Africa, there is a possible outlier between 25 and 30, whereas the UK does not appear to have any outliers. Unusual features. We just talked about an outlier. It's any anything that looks strange about the graph, anything that departs from the normal shape of the graph. So for example, you could have a gap. That's an unusual feature. There appears to be a gap between 3 and 6, or there's an outlier around 9 in that second graph. The second type of graph you can do to display quantitative data is a stem plot. Sometimes it's called a stem and leaf plot. And this gives you a better picture of the shape. It's kind of like a dot plot, but the advantage of a stem plot over a dot plot is you see the actual data values. So you start by separating the observations into stems. So everything but the final digit. So for example, the number 37, 3 is the stem and 7 is the leaf. Right? All the possible stems. So let's say your numbers go from 30 to 60. So all of your stems are going to be 3, 4, 5, and 6, like the tens place. And then all the leaves will be your ones places. Write each leaf in a row to the right of the stem it belongs to. And then make sure that your leaves are in order. Provide a key that explains the context. So for example, 37 and 3.7 are going to look the same on a stem plot, so you need a key to let the reader know which one you're talking about. So here's an example. We've got these numbers, 2, 4, 6, 8, 10, 12, 14, 16, 18. There's 20 of them. Oh, I guess I could have read that up top. There's 20 students, and you ask them how many pairs of shoes you have. So we're going to construct a stem plot right now. The stems range from 1 to 5 because the lowest number is 13 and the highest number is in the 50s. So those are all our tens places. And then we're going to put all of the leaves in order. So 19, 13, 13, 13, 15, all of those are numbers with the 1 as a stem. Now notice how these are not put in numerical order. So the last thing I'm going to do is put them in numerical order. Make sure that every single number is represented. Even though there are 3 13s in our list of data, all 3 of them needed to be represented in my stem and leaf plot. The last thing you need, and the most commonly missed things that people lose points on when drawing a stem plot, is a key. 1 line 3 represents 13. So you have to have a key to show that. So the key 4 line 9 represents a female student with 49 pairs of shoes. So you decide your stems, you add your leaves in order. Now you can let your calculator help you. We learned today how to put our list in order, in ascending order, so that you can easily make a stem plot. When you have too many data points, or if there are, let's say there's 30 numbers between 30 and 40, you don't want to have all of them in one long big line, so you can split your stems. The way you split your stems is you have 2 zeros, 2 ones, 2 twos, 2 threes, and so on. So like 20 to 25 would be in the first 2 stem, and 26 to 29 would be in the second stem. So you can split it up a little bit easier. And you can also do a back-to-back stem plot. Let's say you're comparing 2 different sets of data. So they have the same stems, but the males go off to the right and the females go off to the left. So that'll be useful when you're comparing distributions. If you look at the males and females, the data listed here right now, you'll notice that the female distribution is more varied than the male distribution. And the male distribution is approximately skewed right. If you were to turn that distribution on its side, you can see that distribution better. And don't forget your key. Never forget your key. That is such easy points to lose on a quiz or test. The last type of graph we're going to talk about right now is a histogram. So a histogram is the most common graph you can have. And here's how you make a histogram. Divide the range of data into classes or bins of equal width. Find the count inside each of these intervals that you've created. Label your axes correctly. So the height of the bar is the frequency, the number of data points that fit inside each interval. And the bars should touch each other. They should be next to each other. The only reason you would have a gap in a histogram is if there's a particular interval that has no data points in it. And don't skip over those. You want to leave those gaps. Those are useful when you compare distributions. So here's an example of a histogram. We've got this frequency table here, and our intervals are counting by 5, 0 to 5, 5 to 10, 10 to 15, and so on. We have 50 total data points. So on the x-axis, we've got the percent of foreign-born residents, and on the y-axis, we have the frequency, the number of states that have that percent. So between 0 and 5%, there are 20 states that have that. Between 5 and 10%, there are about 13 states that fall into that category. And so you can see how the distribution of the percent of foreign-born residents is spread out. This distribution is skewed to the right because the tail is skewed to the right. And the range is 0 to 30. There don't appear to be any outliers. And the median percent would be where the 25th data point happens, which is between 5 and 10%. So you would say the median is between 5 and 10%. So since there are 50 states, wherever the 25th state lies, that's where the median is. The 25th state lies in the 5 to 10 range. So we want to make sure we use histograms wisely. You want to be careful that you don't confuse histograms with bar graphs. The difference between a histogram and a bar graph is a histogram displays quantitative data and a bar graph displays categorical data. So you want to be careful about that. Don't use counts or percents as data. So you're not going to categorize counts in an interval. You are counting how many fit into an interval. So use percents instead of counts on the vertical axis when you're comparing distributions with different numbers of observations. So we'll talk more about that later in statistics. You won't use that as much right now. And just because a graph looks nice doesn't mean it's a meaningful display of data. So just be careful of what you're looking at. Make sure it's logical and you're not just graphing something for the sake of having a graph. Is it actually useful to you? That's all we've got for today. Have a good night.